Our next presenter is Kaitlyn, and all that stuff I said in the beginning about quality of character and being motivated for the right reasons and all of that. I think Kaitlyn exemplifies the heart and the core of this group and of what I want the heart and core of CSP to be as a person about as well as anybody possibly could, and somebody that I know pretty well, but I don't know incredibly well, but I feel like maybe some of the same specific or general experiences in life have really made for an exceptional person of exceptional character who's done a lot of hard work here, a lot of learning, and a really impressive job. So as we move to the ocean, it's Kaitlyn and defining marine heat waves in the Southern California Bight, impacts on sea lions. Very charismatic macrofauna.
Thank you everybody for being here. My name is Kaitlyn, and today my topic is defining marine heat waves in the Southern California Bight and impacts for California sea lions. So to start off, here's a quick background of just everything we'll be discussing today. We'll start off with a background of how marine heat waves are formed, the focus area of the Southern California Bight, and marine heat wave impacts on California sea lions. Then we'll look at causes of local marine heat waves, and we'll talk about current policy and protection efforts for California sea lions, and end with future research and conclusions. So to begin, a marine heat wave is generally defined as an abnormally warm water event that can last for months and extend over a large area. And over time, studies have shown that increased atmospheric CO2 can alter strength of wind patterns that are really important to help regulate ocean temperatures. So when we see strong winds, we have high amounts of ocean evaporation, so cooling at the ocean surface. But when we have weaker winds, there's less of this evaporative cooling happening, as shown in this photo. And there's also less surface mixing. So this creates a really thin mixing layer at the surface. So the surface is able to heat up at a really fast rate. So this figure here also represents how marine heat waves occur more in offshore areas, and whereas coastal marine heat waves, these are more influenced by wind direction. So wind direction influences upwelling dynamics of the coast, and here's a quick visual representation of that. So through the process of Ekman transport, these winds that are moving south along the coast will cause waters to move away from the coast due to the Coriolis effect. This will allow the cold water from the bottom to come up and replace that warm layer on top. The process of upwelling not only brings this cold water to the surface, it also brings nutrients that you're going to see here in a bit. And these nutrients are incredibly important for marine life along the coast in terms of food. So with weakened winds and higher temperatures, we could potentially see less of the cold water coming to the surface and less nutrients that can have great impacts on coastal marine ecosystems. So here's some of the more recent marine heat wave events that have happened along the California coast. The blob from 2013 to 2017, 2018 marine heat wave, and the blob 2.0 in 2019. And each of these events was triggered by a change in atmospheric systems that led to weakened winds. So the main literature right now around marine heat waves in this area really just highlights these three events. And the literature also suggests that this string of events may be influenced by early warming of 1982 and 1997 El Nino events. So this raises a lot of questions as to whether are these events just occurring recently or have they been happening over time? And with the recent El Nino event that we just had last year, what does that mean for marine heat waves this summer and next summer? So now zooming in to the focus area of the Southern California Bight, which is located off the coast of Southern California from Point Conception down to San Diego. This area is highly influenced by the California current system, and this system brings high nutrient waters down from the north, so it allows for a very high biodiversity of marine species in this area. Previous studies have shown that increased thermal stratification occurs in this area with marine heat waves, and this further prevents mixing by creating temperature layers that block the colder nutrient waters from coming to the surface. So this figure kind of represents that. So when we have more mixing, we have an even layer of temperature and nutrients are more able to come up to the surface. But with climate warming and this thermal stratification, we have these temperature layers here that inhibit mixing and less nutrients is able to come up to the surface. And being that this area has a high amount of biodiversity due to the CCS, changes in these nutrient fluxes could alter marine life distribution and greatly impact important coastal marine organisms and marine life, such as the California sea lion. So California sea lions are one of the most abundant apex predators within the CCS. They're also considered to be sentinel species, so they serve as indicators of environmental environmental change or health within trophic levels and the broader CCS. So it makes them incredibly important to this area. It's also been seen that with marine heat waves, these events are correlated with mass strandings and reduced birth rates in California sea lions, and this is mainly due to changes in their prey distribution. So as less nutrients are available at the surface, less fish are coming to the area to feed on the nutrients, and less fish are available for the sea lions to feed on, so they end up stranding their young in search for food. However, there is a significant colony off the coast of San Diego that has been overlooked in these studies. And the recent marine heat waves have had a lot of biological impacts on California sea lions, and one of them being shifts in the sea lion diet from a very high energy prey that consisted of more sardines and anchovies to a lower energy prey like rockfish and Pacific hake. And with that, there were massive strandings of pups off the coast of California in 2015, where over 3,300 individuals were stranded. So these impacts bring up a lot of questions about how marine heat wave events affect sea lions in the La Jolla area and the Southern California Bight. So to give just some more background on how marine heat waves are defined, studies follow this standard definition that sets the temperature threshold at the 95th percentile compared to long-term averages and maintains it for at least 5 consecutive days. And basically what that means is, say we're in spring or summer where the average temperature is maybe 20 degrees Celsius for the ocean. If that temperature were to rise to maybe 22 degrees or higher and stay there for 5 consecutive days, this would be an unusual temperature surge and surpass the top 5% of expected temperatures, and this would be categorized as a marine heat wave. However, this definition does not account for global ocean warming. As we know, as atmospheric CO2 continues to rise, the oceans will continue to warm and the averages will also rise. So this leads to our analysis questions. And for our study, we wanted to know, how has the SST warming trend affected marine heat waves in the Southern California Bight? Do El Nino events affect local marine heat waves? And how important is local wind forcing for marine heat waves? And what does that imply about local upwelling? So to answer these questions, we utilized the Scripps 107-year SST dataset, and this dataset worked perfectly for analyzing marine heat waves in relation to the sea lion colony in La Jolla, since the colony is just about 1.5 miles away from where the data is being collected, as you can see from the map. And this record is also very unique in that it may just be the longest SST record for the North Pacific. And here's also just a quick image of the colony, and this is just a part of the colony, just to give you an idea of exactly how big this colony can get. So here is a plot of the Scripps SST data over time up to year 2020. And the gray represents daily SST observations, and the blue line is representing the annual mean temperatures, where the tops of the curves are during summer. And as these peaks get higher, we're representing marine heat wave factors. And in a study by Fumo et al. In 2020, they took this data, and in this figure, they plotted over a year with 20 degrees Celsius being the 95th percentile, represented by the pink arrow. And they counted the number of marine heat wave days above that threshold with temperatures lasting 5 or more days as marine heat waves. And that's represented here by the colored sections. And you can see that this is really occurring over spring and summer. So for our project, we revisited this method to ask our questions about potential forcing factors for marine heat waves. So we took the SST data and we plotted it over the 107-year record, counting the number of marine heat waves that lasted for 5 or more days being a marine heat wave event. And I also here just pointed out with the arrows showing those three recent marine heat wave events, the blob, the 2018, and the blob 2.0. So our top bar plot shows increasing marine heat waves over time, and this coincides with the gradual ocean warming. However, our bottom plot, when we remove the long-term warming, we have a more even spread look at the marine heat wave events, and we can see that these events have been happening all along, but they are becoming increasingly hotter with global warming. So further, here's just another bar plot showing the same thing from before, our increasing marine heat waves over time, and this is with the global trend on top. If we were to assume that this global warming trend will continue, we can project this data out to 2040 and apply the new trends. And in doing so, we would see extreme warming. So with years having up to 300 days being considered marine heat wave days. So this raises a lot more questions about what marine heat waves will look like in the future and impacts for California sea lions. But as we think about it right now, as these temperatures are continuing to rise, we could potentially see more northward migration of the sea lion communities to colder waters. So in terms of population dynamics, the Seal Society of San Diego was kind enough to share their sea lion population data with us. And this is data retrieved by means of volunteer and drone counts. So the data really depends on how many volunteers are able to help at a time. So the Seal Society currently only has about 2 years of data, and these plots show data from 2023, the 2023 population counts in different areas of La Jolla over time. So even though there's very little data here, we can still see that the population is seeming to remain fairly constant over the year at about 230 individuals from April to December. So as this data is right now, it doesn't really show how marine heat waves have impacted this population, but with more data, we'd be able to better understand this colony and how marine heat waves might be impacting them. And in terms of current policy and protection, California sea lions are currently protected under the Marine Mammal Protection Act of 1972 through NOAA. However, there is a lack of NOAA attention to the La Jolla colony, as this colony is thought to not be in need of protection currently. But according to the IUCN classifications for protection, most sea lion colonies should be classified as endangered or vulnerable. However, California sea lions are not listed as endangered or threatened under the Endangered Species Act. So in means of protection efforts, the Sierra Club and Seal Society of San Diego are working to advocate to close certain areas in La Jolla during pupping and breeding seasons to protect California sea lions from local tourism efforts. And they also bring up the important fact that this is one of the only rookeries on California's west coast that's in an urban environment, and it brings significant tourism. So any declines in this colony could potentially have some socioeconomic impacts as well. However, there just simply is not enough data for this colony to declare them a rookery. But with more population data and possibly declaring them a rookery, we could bring more protection efforts. So coming to our conclusions, we have found that wind forcing is an important factor for local marine heat waves, having impacts on nutrients and food supply. Future studies would benefit by looking at the difference between early natural El Nino events compared to the global warming signal to further evaluate impacts on California sea lions with projected extreme warming. Collecting more population data for La Jolla sea lions can not only help us assess changes in the population and marine heat wave effects, but it could also help achieve more protective measures for sea lions against growing climate change concerns. So thank you so much, Mark, and my chair, Mark, for all of the help, Marin, for all of the help with the plots, and the Seal Society for the interviews and learning about what they're doing to help protect California sea lions. And here's my references, and thank you so much for your time. Annalise.
I'm just curious because I don't know what it is. What is a rookery technically?
A rookery, as far as I know, is a colony that is of significant size that breeds in a specific area, and that is their main home, is what I would consider it to be, and that's their rookery. Yeah. Yes.
What leads to the stranding of the pups?
Yeah, so it kind of all really has to do with that nutrient availability. So if there's less nutrients around, there's going to be less fish around. So when there's less fish and the sea lions need food and it's not in their vicinity that they normally get it from, they end up leaving at further distances to go and find this food and end up leaving their pups. So their pups have a lot of complications. And I did find there were a lot of complications with the pups, with the strandings. It was pretty sad. Yeah. Yes.
Could you go back to your chart about the projected heat days to, or sea surface heat days to 24? Yeah, that one. That doesn't look right to me.
How so?
20 to 40. I mean, is that just the only thing that trends there is the tops of the highest ones?
So we basically took the warming trend that we see with the background global warming, and we assumed that it was going to repeat itself. So we just took that trend and replicated it over time. And this is what it would look like if the trend were to continue warming as it is now. But it's much more complicated than this because we don't know what's going to happen. We don't know what's going to happen tomorrow, right? So predicting these events in the future is very complicated, and it would benefit us to look at this without that background warming trend, because then we would have that more even spread look and kind of get a different idea of that. So,
Thank you.
yeah. But thank you very much, everybody.